Good morning. My name is Pratyai Sarma. The topic of my BTP is high voltage portable pesticide spray under the guidance of Aditya Bandyopadhyay sir. The main principle used in the experiment is electrospraying. Electrospraying is the process of formation of small droplets from the bulk liquid surface under the presence of very high voltage of the order of kilowatts. It was first studied by Rayleigh when he studied the instability of a charged droplet. Data spraying involves the formation of a cone jet at the liquid interface, which is known as the Taylor cone. It has been used extensively for mass spectrometry and for various biomedical and pharmaceutical applications. Application of electrospraying to pesticide industry has extensive possibilities. The conventional pesticide sprays have very low efficiency due to the drift of the spray. It also leads to human health risk and pollution of the environment. Electrospraying is highly target specific and hence it can reduce drift losses, thereby increasing the spray efficiency and minimizing the spray cost. Much work has been done in this field in the past. Jamadar et al. Have presented a general idea regarding electrostatic spraying and its application. Work has been done in CSIR-CSIO on development of nozzle for pesticide spraying and also on the optimization of the various performance parameters associated with it. Maskey and Duraras have shown that most of the spraying requires a suitable device for the charging of the droplet. So our basic objective is to develop a circuit for the production of the high voltage. Then we observe the behavior of the droplets under the application of this high voltage and analyze the results. So the basic experimental setup is as shown in the figure. It consists of 5 main parts. We have the high-speed camera, which is used for viewing the motion of the droplets. Then we have the syringe pump, which provides the different flow rates used in the experiment. Then we have a hollow stainless steel needle and a metallic plate, which are placed beneath each other. And we have the high voltage source, which provides the high voltage used in the experiment. The liquid used in the experiment was 1 millimolar KCl solution. The procedure for the experiment is as follows. The needle and the metallic plate was fixed at a certain height, and then the two ends of the high voltage source were connected to the needle and the plate respectively, and so they function as the electrodes. The syringe pump was connected to the needle and the flow was started. The imaging of the droplets was done with the help of Frontech fast motion software. The experiment was repeated for flow rates of 10, 20, 30 and 40 ml per hour, and for separation between the needle and the plate of 3 mm, 7, 11 and 15 mm. The high voltage source which we have designed for the experiment consists of 4 parts. It has a lithium-ion battery which gives an output of 5 volt. It has a LG105 high voltage module which gives high output voltage of the order of kilovolts. Then we have the current limiting resistor of 1 ohm 1 watt capacity and a switch. High voltage module which is used in the high voltage circuit is basically a complex circuit for a conversion of DC voltage from low values to very high values of the order of kilovolts. It is basically a combination of a DC to AC converter circuit, a transformer and an AC to DC converter circuit. The AC to DC converter circuit is basically a Cockcroft-Walton multiplier. So we found initially that as soon as the circuit was switched on, the large droplets broke down into various tiny droplets. It was found that a droplet of around 0.96 mm diameter broke down to form droplets of around 0.20 mm diameter. Also, the surface of the liquid was found to elongate to a large extent, and a wobbling of the liquid surface was found before the droplet was ejected. This could be attributed to the fact that as the potential is applied to the liquid surface, the charges start accumulating on the surface, and they cause the surface to elongate till it reaches a certain limit called the Rayleigh limit. We then fixed the electrode separation and took the observations for different flow rates from 20 to 40 ml per hour. It was found that the size of the droplets increases with the increase in the flow rate. This could be attributed to the fact that as the flow rate increases, the inertia of the droplets also increases, so that a large volume of liquid is ejected at a time, and hence the size of the droplets increases. Also, it was found that the sideways movement of the droplets increases with the increase in the flow rate. The spray was found to be intermittent for lower flow rates, and it becomes continuous as flow rate increases. This is due to the fact that as flow rate increases, a larger volume of liquid is accumulated near the tip of the nozzle, which makes it more easy for the droplet to be ejected. Then we fix the flow rate and varied the electrode separation from 3 mm to 15 mm. It was found that the size of the droplets decreases with increase in electrode separation. This is due to the fact that as the electrode separation increases, the electrode potential also increases, and then the charge distribution on the droplet increases. This increased charge distribution overcomes the interfacial tension of the liquid droplet, and the liquid droplet has to shrink in size in order to maintain stability. This causes the liquid size to decrease. We also found that the sideways movement of the droplets increases with the increase in the electrode separation. Also, the spray was intermittent for lower electrode separation and becomes continuous as the separation increases. This is again due to the fact that as the separation increases, the electric potential increases, and hence the electrostatic repulsion between the liquid surface and the droplet to be ejected increases. As a result, the droplet is ejected more readily. Some unusual observations were also found during the experiment. In some cases, it was found that the droplet, after getting ejected from the liquid surface, again moves back upward into the surface. Also, in some cases, the droplet was found to move horizontally instead of moving vertically downward. In some cases, it was found that some larger droplets were ejected in addition to the normal smaller droplets which were ejected during the spray. We then proceeded to calculate the diameter of the droplets to verify our previous observations. For this, we made use of the MATLAB image processing toolbox. To find the diameter, we first needed to detect the edge of the droplet. This was done using the Candice method, and thereafter we found the diameter by using the formula D is equal to 4A by P, where A is the area of the droplet and P is the perimeter of the droplet. As seen here, the diameter is found to increase with the increase in the flow rate and decrease with increase in the electrode separation, which matches with our previous observations. Another important parameter is the angle of ejection. It is the angle over which spraying occurs from the nozzle. The angle of ejection for the various combination of flow rates and electrode separation are tabulated as shown. We also constructed a phase plot to show the different modes of spraying of the droplets. Here we can see the different spraying modes like the vertical spraying and the sideways movement of the droplets and the horizontal movement of the droplets. Also the formation of some large droplets, mainly for the larger electrode separation. We also tried to get the evolution of the droplet. For this, we first detected the contour of the droplet using edge detection. Then we overlaid the successive contours of the droplets into a single frame, which gives us the evolution of the droplet. The droplet evolution has been shown here for the 3 mm and 7 mm separation for the different flow rates of 10 to 40 mm per hour. The time delay shown below the images is basically the time difference between the successive contours of the droplets which are overlaid. Thus, in this experiment, we have taken a look into the various behavior of the liquid droplets in the presence of high voltage. The observations were found to be in accordance with the theoretical results generally. Some unusual observations like the upward and horizontal movement of the droplets were also found, which need to be looked into. Future work could include the modification of the circuit by replacing the switch with an optocouple and transistor so that the circuit could be automated, and also making suitable changes to make the device portable and ready to use. Thank you.